All right. Remind me, what's a protocol? Language. Language that two things use to talk to each other, right? So fancy name for that. We've been talking about web servers. We've been talking about HTTP. At the end of class last time, we were talking about kind of how the internet works, right? So we mentioned this thing called DNS. We go back just a little bit further. So we mentioned TCPIP. We mentioned sockets. How far back do we go here? All right, so we have handshaking. So we use the example of modems talking to each other, making all those beeping noises. What are they actually doing when they're beeping and stuff? They're negotiating a maximum speed over which they can transfer stuff without mistakes because they were not governed by TCP/IP. Well, now they are, so TCP/IP has a goal of ensuring data arrives at its destination. We did talk about two different kinds of sockets last time. We talked about the generic socket being a communication channel that sits between two links on a network. Think of it as the internet today. TCP versus UDP. When would we use UDP packets or UDP sockets? What are some example applications that would use UDP? Streaming videos where one dropped frame or something like that isn't at the end of the world. It would be far more inconvenient for us to have to wait. Video pause, have to wait for them to retransmit that one frame that we may not have noticed. But when we're using, when we're downloading a file and we need all the bits got to be there, we definitely want TCP to be governing that transmission. All right, so these are sockets. One is not necessarily better than the other. They are just solving different problems. Okay. What's a MAC address? We mentioned this last time. So really, it's every network-aware card, network card has a kind of a unique serial number, if you will, kind of social security number for it that allows it to be uniquely identified anywhere. We talked last time about you have some networking tools that allow you to spoof a MAC address to pretend like you're a different MAC address, because MAC addresses are often used by DHCP to hand out a IP address, so you get the same IP address multiple times. It's convenient for the DHCP server. Did we write DHCP down here somewhere? I know we said it out loud. Remind me, what is DHCP? Dynamic Host Control Protocol. What does this guy stand for? Or what does this guy do, rather? So, hands out IP addresses to machines requesting it. Why is that better than each of us just putting in a manual IP address? Yeah, because if two of us put the same IP address down, even if it's a legal IP address on the network we're on, those are going to conflict with each other, and it's actually even worse on a Ethernet-based network, which is a bus-based network where basically you just got a bunch of traffic flowing through, and you kind of dip down and see, is this for me? Well, you got two guys that are thinking it's all that network stuff is for them. All right, so, but from our perspective, we don't necessarily care about all this network mumbo jumbo stuff from a, we're not building a network here that's going to hand out IP addresses. These are more networking course characteristics or more of an IT professional background, but we are kind of interested in that protocol aspect of this. We're seeing lots and lots and lots of examples of little custom languages, domain-specific languages for communication between various systems. Okay, now that starts sounding like it's related to systems programming, right? Us being able to talk to these things or even create our own little versions of these. So at some point in time, somebody created a system for handing out IP addresses, right? Okay, and they decided, okay, here's the chit chat that's going to have to go on between the host and the server to, this guy's going to ask for an IP address. This guy's going to kind of make sure that you're legitimate or whatever. And he's going to hand you an IP address and he's got to mark it off. All these little things have to happen. And we're solving a little tiny problem, but it's a very important problem. All right. So kind of lots of examples of protocols all over the place here. We were talking about DNS last time. A DNS is a distributed system. What do I mean by a distributed system? What does it mean for a system to be distributed? Somebody who hasn't answered today yet. So, okay, one machine's not responsible for everything, so we're distributing the problem across multiple machines. And so if we type in www.google.com here, go down to the lab there, press enter, that request, I mean, at the end of the day, we have to map that to an IP address because that's the way the internet works. The internet ultimately says, I need the unique phone number, if you will, the unique IP address of where my destination is. And then we have to consider that there's all sorts of magic stuff that happens in between that actually gets our request from here to there through all these different networks and stuff like that. But we need the GPS location of that guy. So this is really not necessarily dissimilar to when we are typing in the address for some road trip, and we're putting in I navigate by restaurants. So like when I'm coming back to the Mequon area, if I know I need to drop my buddy off, I put in Mequon Culvers because I know he's close to there, right? Because I can quickly look that up on Google Maps. Just do Mequon Culvers, and I don't know what the address is of Mequon Culvers, but I've gone there a whole bunch of times using my GPS. That's getting mapped to actual GPS coordinates, right? DNS works similarly. We type in something we can remember, google.com. DNS is then mapping it for us to an IP address. Now the question is how does it actually do that mapping? Are there lots and lots and lots and lots of domain names out there? Yeah, a whole bunch of them. Now, I don't actually know the answer to this, but we can make a reasonable guess. If we had to store all of those mappings, the domain name to the IP address, is that probably a lot of data? Okay. Now, how many people at any individual point in time are requesting that mapping? How many people are pressing enter in their computer right now on a web browser trying to convert between a web address, a domain name, and an IP address? A lot. Okay, so not only is there a lot of data to map between, we have a lot of people this exact moment who are all trying to do that because we have a lot of people all using the internet at the same time. We're not even talking about going to the same site. We're talking about people using the internet, which requires a translation between the domain name, which is kind of human readable, and the IP address. So that would require a lot of horsepower in order to do all that at once. So the DNS system is a distributed system. So the DNS server here at Concordia is our first line of defense, if you will. They're the first ones that try to help us. All right, so they've collected kind of a local list. This isn't necessarily all the domain names that have ever existed with the mappings, but a local repository that represents some fraction of all the domain names, but maybe helps with 90% of requests that we make. Because don't you think that probably 90% of the sites that we go to on campus are probably repeats, probably been there before? Whether it's you individually or somebody else on campus, that kind of stuff. All right. So when we type something in, the first thing that it goes to is it tries to jump to Concordia's DNS. And Concordia's DNS tries to look it up in their little database because all they're having to service is all the people here on campus who are using Concordia's DNS servers. Now, regardless of how many simultaneous connections that is, I mean, there's plenty of people in the last 5 seconds that have pressed enter on their web browser here on campus to try to translate from one domain name into an IP address, but far, far, far less than in the whole world, right? So we're going to say that as long as Concordia's machine is kind of beefy enough, it could probably handle the Concordia community for doing that mapping. And then if it can't do it, it throws it up to the next level, the next distributed level of DNS that hopefully knows more than Concordia's server does. So kind of Concordia's DNS server is a subset of its boss, which is going to be a regional DNS server. And that's actually, we don't know how many DNS servers might be within DNS servers because they become children of each other. So we're just going to assume it's a regional because the details of it aren't that important to us. So let's assume it's a regional one. If the regional one doesn't know the answer, because it's handling all that, if we assume that 90% rule, that the local DNS servers know 90% of the stuff. It's handling the 10% overflow, right? That bounce up there. So it's hopefully handling an amount of requests that it can handle. And if it can't handle it there, then it's bouncing up to the next level until we finally get to the top where you have like 6 different duplicates of all the domain names that exist. That's where they get registered with. But you kind of understand the reason why we have this problem distributed across the world, so that we try to capture most of the traffic at a local point, so that we don't have everybody in the world all getting served by one single server. I think I mentioned last time, sometimes one thing that might be handy for you to do, if you maybe throw like Google's domain name or Google's IP address into a browser or into a file somewhere. Let's just look that up here real quick. So let's see, well, let's just do google.com. Just do IP mapping. Actually, let's do this. All right, 192, 149, 245, that's our big domain name. So let's look it on www. Oh, that's actually non-routable, so we need a routable one. So these are Google's DNS servers, 8888 and 8844. What is the address to Google? IP address. Just want a fake IP address real quick to use. Well, okay. This is actually using DNS. I guess that's a reasonable thing. So there's the IP address. So that should take us to Google's website. So if you store that IP address in a file somewhere, then if your internet seems down, you can go ahead and try typing that thing in, press enter, and if it gets you to Google's webpage, then your internet's not down, your DNS server is down. So then what you might do is you might store a couple of other DNS server IP addresses somewhere and then have backup DNS servers on your networking, so you fail over to that in the event that your current one isn't working. But just a point of reference for how those lookups actually work. All right, so last time we were kind of talking about how our actual web servers work, and that when we do a search at Google, we don't have to wait in line for the next person, right? So we kind of created this idea of well, there must be some sort of technology that's involved that allows one person to hit Google, and then something happens at Google's web server where that person can start getting service while the next person is being served as well. Make sense? All right, so, and that's kind of what this distributed denial of service attack stuff is all about. It overwhelms the server by hitting it a zillion times. Those things wouldn't work if a server only tried to serve one person at a time. The fact that our servers try to serve multiple people at once, we start running into this issue. So let's look at how this model actually works. And we actually could probably talk about it in terms of this class right here. So we're going to say that these folks over here are going to be my worker bees. So call this multiprocessing. So in the old days, we would create a we would create a new process to handle the request. All right, so we're going to pretend for a second there's going to be a curtain up here. So none of these folks are even born yet. All right, they're not there. All right, so you have an incoming connection. I'm Google's web server. So incoming connection comes in. We're talking the HTTP protocol, but I don't want to waste any time because she's going to be making a request here in a second. So before I do anything else, okay, Brennan has been born. Right? He's come into existence. Everything's good. He's actually a duplicate of me. Okay, Brennan's a duplicate of me, but he's going to look within himself and say, "Oh, well, I'm just like my parent," but he has to know that he's the parent. And this is done from a system call level with something called fork. All right, and this is where things start getting a little funny. We need to be very careful to enunciate. All right, because effectively what I just did is I just forked a child process. Okay, you can kind of see where this is going. All right, so the fork system call, and we're going to see this at the Unix side. And here I can actually open up my terminal here again. I'll just kind of show it to you out here. It's even worse. Man is the command for manual page. All right, so we're going to be using this before too long. So this is a header file that we'll be importing into our C programs. So this is a function call, fork, and this guy returns a process ID. So on an operating system, every single process that's running has a unique identifier on that operating system. Okay, and there's a finite number of unique process IDs that can exist in an operating system, and it's typically bound by the size of like integer, something like that, or maybe it's the size of a long. So just as an example, let's just assume that we're dealing with a somewhat modern operating system, and maybe that operating system has a maximum number of simultaneous processes of 65,536. All right, so that's the size of an unsigned short. So it's a 16-bit value, right? 0 to 2 to the 16th. Make sense? So we got 65,536 unique process IDs. Now, every single time somebody double clicks on an icon, for example, or starts a program in some other way, a brand new process ID, a unique identifier for that process is born, right? So I was maybe process ID 1. I was Google's web server. And then I forked Brennan. Yeah, I was gonna have trouble not giggling at this. Okay, so now we have a brand new process ID that was born. So maybe your process ID 2. Okay. Now the way distributed denial of service attacks works, well, really any denial of service attack, is they might keep hitting this web server, causing me to spawn new child processes. What happens once I've spawned 65,536 unique processes? Operating system doesn't support anymore. Right? So what do we have to do? Well, it actually becomes very interesting because now you have an operating system. So the denial of service is now done, right? Because I can't, I'm going to keep getting fails when I call the fork system call. It's not going to work anymore because I've already created the maximum number of process IDs. So how do we fix this? We got to kill some. Good, I'm glad you went there. So how do we kill a process? Well, so the Unix system admin comes in here. He opens up the terminal. Maybe he looks at all the stuff that's currently happening on the machine. Here's the process ID of that guy. So, for example, let me just copy this guy right here. I'll open up a new shell window. I'll go ahead and kill that process. You'll see that back here, it's ended, so I killed off that process. Why wouldn't I have been able to do that? Yeah, when I opened up this terminal, that required a new process was born. It's always very interesting when you have a system administrator who's got a physical computer sitting in front of them that they can't access. Why can't they access it? They're going to double click on something, it's going to make a new process ID come into existence, right? So sometimes they have systems that maintain a terminal connection that's always open. So it's already reserving a process ID, so that's not one of the other guys. Sometimes you can connect in directly through a serial port if you're dealing with an operating system that will allow, which actually effectively has a hardware process through a serial port, whatever, unimportant. But, you know, real fix might be just turn the computer off and then back on again. That'll clear out all the process IDs. Why might that be bad? Maybe for us, most of the time that's no big deal, right? Inconvenient for a couple minutes. What if the machine was in the middle of a backup? Or was in the middle of a restore, or was getting ready to do something else that was really important that really requires the current state of the machine's memory to be intact in order to do it. And if you reboot it, you're losing some real data, stuff like that. All right, so we can see that that's why denial of service attacks become kind of problematic things, but they all ultimately are based on the total number of process IDs that a machine can have, right? Well, so what do? We say, oh, well, you know, maybe we just allow more process IDs. Well, so then we just distribute the problem to more machines and all hit it. So now you'll run out of that more number of process IDs. Rinse, lather, repeat. All right. So in any case, if we're thinking about how a web server actually works, if I'm Google's web server, under normal conditions, what happens? You make a connection here. I effectively use kind of like the phone is ringing, right? I pick up the phone, I go, hello. What's he saying to me? What language is he speaking? HTTP. He's speaking the hypertext transport protocol. So we're going back and forth with that protocol. But actually what probably happened right off the bat is I picked up the phone, incoming connection, spawned a child process, handed that phone to Brennan. Brennan is now dealing with you. Well, I kind of handed the socket to Brennan for him to deal with that communication. And then I'm waiting by the phone again for the next connection to come in. And all that happens very quickly, right? Some fraction of a second. Next connection come in, I pick it up, spawn a process, hand the socket over, wait by the phone. Okay, now as soon as you and Brennan, so you've now made a request for index.html. Brennan goes and looks it up, finds the thing, spits out the HTML and JavaScript to you. The job is now done. Brennan dies, okay, right? He kicks the bucket. The connection is now severed because there's not an ongoing connection between the two of you. And the next time you request something, you're going to open up a new connection. Now we might look at ways that we can be more efficient here. Right? We might say, well, maybe Brennan shouldn't just die because it does take some resources to create a new process, and we would assume it takes some resources to kill off a process. And he's a perfectly good process that knows how to deal with incoming HTTP clients, right? He just doesn't have any work to do this very second. So maybe he kind of becomes my pool of processes over here. So instead of me having to create a new process every single time, it might be more quick for you to open up a connection. I have the socket, I just hand it to the next guy in line. That make sense? Something like that might be kind of how the process works. All right, so now a little bit ago, I mentioned something about this fork system call. So this guy creates a duplicate of the current process. And let me go back here to the man page for this. Here's the return value. So upon successful completion, fork returns a value of 0 to the child process. All right, so I've mentioned that. Let's just look at a picture of this. So if I'm the parent process here, so this is www, all right? And this guy has a real process ID. Let's just assume he has a PID of 1. Okay? When the fork system call gets called, so this guy's programming, we have a new incoming connection, this guy runs the fork system call, he creates a duplicate of himself. Now, if we're looking at the 1,000-foot view, we can actually see maybe that this guy actually has a different process ID. Make sense? But these two, they don't actually know, they don't know who's who. They don't know who's the real one and who's the clone. Because if we're looking at the code here, we hit that fork system call, then we're going to say if PID is equal to 0, I'm the child. Else, I'm the parent. This is the exact same program. When we used the fork system call, we actually made a complete duplicate of the current process. It's picking up from the exact same line as the other one. So we finished this line here, so now we're sitting right here. And then this guy asked the question, who am I? Based on the result of the fork system call, I have a value inside of my variable called PID here. Is that value a 0? If it's a 0, that means I am the newly created child. So I should do child-related stuff, right? And in this case, what was Brendan supposed to do? He was supposed to have an HTTP conversation with Muath about incoming, about requesting index.html, that kind of jazz. All right? Now, if I'm the parent, if I'm the original here, what do I do? Wait for the phone to ring again, right? So this whole thing is probably inside of an infinite while loop. So while the phone's not ringing, wait for it. As soon as the phone rings, pick it up, fork, hand the socket off to, so this is probably where I'm handing the socket off to the child. Otherwise, spin back up and wait for the phone to ring again. That make sense? Go ahead.
If it's the parent, couldn't it also be an error that there wasn't a possibility of being able to make a process?
Yeah. So we go back and look at the documentation here. Here's the possible error. The system imposed limit on the total number of processes. We're going to give you does it actually tell us what the values of these? So these are enumerated types. So it's going to be some global value on the operating system that you probably would want to check to make sure that the PID you got back was actually you. Because the generic version of this is when we create the duplicate process, PID equal to 0 is the child. PID not equal to 0 is the process ID of the newly created child. Right? So if I'm the original parent and I create a child process, so this new process is born, Brennan gets a PID of 0. That's his way of knowing, I'm the clone. So I should do clone stuff. Where I'm going to get Brennan's actual process ID. Does that make sense? What can I do with that? If I have Brennan's process ID, what can I do? Well, I can do all sorts of stuff, including kill him, right? But maybe that's my way of communicating with him, sharing some memory with him, stuff like that, things that we're going to do this semester. But maybe the nastiest thing I can do is I can kill him. I am in control of his existence. He doesn't know about me. As far as he's concerned, he's looked around and he's there. Okay? And he's in the middle of a program. He doesn't even know how he got there. Recognize it, I'm the clone. I have very little to do with what's going on here, but I'm supposed to pick up where I left off. Why? Because somebody else can kill me. All right? Does it kind of start making some sense now? Okay, so at the high level, we're going to do this in more detail when we actually go and write our own web server, but at the high level, Do we have a pretty decent idea how the fork system call works? Okay. Now, at the end of the day, notice that fork creates a duplicate of the current process. So ultimately what it's creating is a new process. So we ask the question then, what is a process? So think back to your operating systems class where you talk about process management and things like that. What is an actual process? Okay, well, what we talked about in here at the very least, it has a unique ID, right? So they have a process ID. Okay. What else? Could we say that a process is a data structure? Or even more generically, could we say it's represented by an object, a class probably, that has some attributes associated with it, that has some magic tricks that it can do, functions and things like that. So at the end of the day, is that pretty much it's a data structure. It's a structure for holding data specific to what a process needs to hold, right? You know, when we took 300 and we talked about data structures, we kind of talked about the historical, traditional data structures, linked lists and stacks and queues and things like that. But the reality is there's data structures everywhere we look. Right? Any structure that's built for holding data is technically a data structure. It just might not be one of the famous ones, okay? Which is fine, or one of the primitive data structures, since linked lists are kind of the primitive building block for any singly linked data structure, or linearly linked data structure. So a process has a process ID. Now, how do processes get processed? Who do they have to interact with to get processed? CPU. All right, so what does the CPU do? Do I ever have a thing on CPU in here? Okay, so let's remind ourselves of that. So what's the CPU? I always like when I ask the question, what is something, and they just define the acronym. Central Processing Unit. So kind of the least important part of it is what does it stand for, right? Because we've already kind of covered that in everything, but certainly in technology, we're famous for this. We come up with acronyms that make things sound way more complicated than they are, right? That's how we demand the big bucks. You know, DHCP, HTTP, blah, blah, blah. You just spit stuff out and the other person is right over their head. That's it. 3 things.
That's on my head. In grade 25, we talked about it as a magician with magic tricks.
Yeah, that's got to be the correct answer since it came out of my mouth. Everything's gold. Yeah. So this guy, collection of magic tricks, where each, well, here, the way I've been explaining it more recently is, when I'm teaching in some of the beginning programming classes, is have everybody raise their hand. This would be a good exercise for us. Hands up. All right, now wiggle your thumb. Did everybody do that? I thought I was the only one. Okay, how many? Okay, move the index finger. We all do that? Now, how many of you are impressed I can do this? I'm doing it a little bit faster than some of you. And what about waving back and forth like that? You all, man, I thought I was better than this. So we all can do these little tiny things. Are any of those things impressive in and of themselves? Do you ever walk up to somebody and, kind of wave at them and then just expect them like, oh my gosh. Just like they saw one of the people in like the Olympics do the backflip on ice skates. And see, that's amazing, right? The good news is I probably wouldn't hurt myself. I wouldn't be able to get enough rotation. I would just land on my back. That'd be like fine. But like the people that can almost do it, they landing on their head. But nobody's impressed. Nobody's impressed if we can just wave our hand and stuff. Yeah, you're a person. You can do that, right? So why is this movement important? Why is this movement important? What does that let us do? Yeah, if we do these little tiny, unimpressive movements, we do enough of them in the right order, with the right timing, we can actually accomplish real tasks. That makes sense? CPUs are like that. They have a whole bunch of what I've referred to as magic tricks. Okay? Little tiny, maybe unimpressive little magic tricks that solve some tiny, tiny, tiny little problem. That in and of itself may not be very impressive. But when you put enough of them together in the right order, something magical happens. Okay? That's how the movie Frozen was made. Right? You didn't like Frozen?
I hate Frozen.
Really?
I don't like Star Wars either, so don't talk
What
to
does
me.
Frozen have to do with Star Wars?
I was just thinking
So my wife and I have that same joke. If you watch Big Bang Theory, Sheldon and Amy. So I'm a lot like Sheldon, especially at home. I have some, but my wife, she's also a nerd, but it's like her job, not her life. So she's kind of like Amy. So like my wife, she won't get a lot of the references I'll make, and it's like, what are you, Star Wars? And some of the quiz things that Amy does, where like that's a valid answer to some quiz question. Are you Star Wars? When Sheldon is like trying to find out what kind of my fruit or something like that. You got to watch the show. You're missing out here. All right, so do we have a decent idea what a CPU is now? All right, so whole bunch of collection of magic tricks. Now, how does a CPU interact with a process? So if we're going to draw a picture here, we have our CPU. And we had a picture up earlier, I think, that kind of showed the CPU scheduling and stuff like that, right? So we have a whole bunch of processes lined up for multiple CPUs, whatever, blah, blah, blah. Who cares how that CPU gets onto, here, I'll actually steal one of our processes here. All right. We don't necessarily care how this process ended up becoming next in line for the CPU. That's an operating system thingy. All right. Fine. But he's there. So this process and this CPU are working together to have something get accomplished. And we're trying to figure out, what is this guy? And we've represented him as this red box here, but we kind of appreciate that under the hood, he's a data structure that holds on to a bunch of stuff. Right? We decided that one of those things must be a process ID, a unique identifier. So we know that this guy has a certain process ID, where another process that lives on the operating system at the current time might have a different process ID. So we care about how these two dudes are interacting with each other. Who's in charge? Well, in this relationship. So the processor is fed. So we kind of think of this like a monster. And this is the monster. And somebody shoves the process in until just leave us alone. Okay, he throws it in there. And now the process has been loaded onto the CPU, ready to be fed upon. It's very kind of a vampiric type of, actually in some ways it is. We'll have to make that connection. All right, so in any case, this CPU is feeding off this process. What does that mean? How is it feeding off the process? What is the CPU eating? Instructions. All right, so if we go back to what's a process, this guy must also have a collection of instructions. What's an instruction? Where did it come from? Okay. So we have the birds and the bees of instructions. How is an instruction born? Don't go too creepy with it. Just keep it at like, kind of the sort of funny level. How is it, as programmers, okay, ultimately, human beings are writing some code, right? At least right now, we're getting to the point where maybe machines with machine learning are going to start reprogramming themselves. But right now, we still are mostly in control. All right, so we write high-level code. That's what gets shoved into the computer, high-level code. And then what happens to that high-level code? In fact, I'm going to draw this as a picture instead of typing it here, because I like pictures. Okay, so we have our high-level code, which then goes through a compiler. And what does the compiler do? Almost. Translates it into low-level code, something like assembly language, right? So we write our C++, then run it through the compiler. Compiler spits out assembly language. And we've seen assembly language before, right? Did we relook at like Hello World in here? So we kind of saw how operating system. Yeah, didn't we look at syswrite in here? You lying?
In this room, yes.
Okay. Based on time, let's actually look at that real quick. Okay, so most of you hopefully remember this from one of my classes, but it's more meaningful to us now because we're actually working at this level in this class. All right, so if you write hello world in C++, let's say, you would say printf hello world. Done. Got a couple little things on either side of it, but it's really one line. High level, high level program. You just write printf hello world and life goes on. Java it's system.out.println hello world, life goes on. That goes through the compiler and this is what gets spit out. Okay. Now this is specific for the Linux operating system. So we've been kind of referencing operating systems here and we've been talking about Unix and we're going to be using Unix in here and we're going to be using a Linux distribution, which is a open source version of Unix, whatever, same thing, let's say. But for us, this is going to be very meaningful. So we compiled our C program on Unix, and it turned it into this assembly language code. Okay? And what is this assembly language code? This is how our instructions interact with our operating system. Because a big part of this here, like we look at this, it's like, oh, okay, well, this is a little bit scary looking, but this isn't that long, right? Like a human being could write this. There's a gigantic power tool sitting in here. One's right there, the other one's right here, where the operating system has a really scary looking program that we're calling, but we didn't have to write in order to make Hello World work. So just to review this real quick, and I'll go pretty quickly since we're seniors here, is these first four things are just moving pieces of information into different memory locations. We're effectively staging data for our big finale, okay? So we have a couple of variables down here. So we have the message, hello world, and then we have another variable called len, length, and this is the length of hello world, all right? Two pieces of information, the message itself and then how long the message is. So we're going to throw how long the message is into this little memory location. That's a hardware register. We're going to throw this piece of information, the message itself, into this hardware, this memory location. Then we're going to just randomly throw a 1 into this memory location. And we just happen to know, as an assembly programmer, or the compiler happened to know, that in Linux, the 1 represents the file descriptor for something called standard output. All right? Or you've seen it in Java as system.out. That's standard output. So most operating systems, most modern operating systems have, it's actually a POSIX-based thing, has three streams, three default streams. We have standard input, which is the keyboard, standard output, and standard error. Okay? Why do we have standard output and standard error? Even though by default both of those go to the screen, they're two separate streams because you might choose to redirect standard error to a file. For instance, log files for errors. Okay, so that's why it's separated like that. So what are we saying here? We're going to move the file descriptor for standard out into this memory location, and then we're moving number 4 into this memory location. And number 4 just happens to correspond to this gigantic power tool in Linux called syswrite. Okay, it's a scary program that was not written by you that knows how to do all the magic of getting some crap up on the screen. All right, so that you don't have to write it, even at the low-level language level. All right, so we just moved we haven't done anything yet. We just moved 4 pieces of information into some buckets. What happens next? Now we interrupt the CPU and we tell the operating system to take over. So what happens? The operating system immediately looks at EAX and says, what do you want me to do? I'm doing a sys write. Where am I writing it to? Looks in EBX, I'm writing it to standard out. What am I writing? I'm writing this message right here. How long is it? It's this length right here. And it goes and does its thing. Then, this guy has left the CPU to do I/O stuff. Now he gets back onto the CPU. So syswrite was actually a program that had a process born for it, which had CPU time that actually did this stuff. Okay, but now this guy gets back onto the CPU. We overwrite what used to be an EAX, which was what we wanted to do, with a 1, and 1 just happens to correspond to the Linux system called system exit. Then we go ahead and interrupt again, and it just so happens, so when we interrupt again, Linux goes and looks in EAX and says, what am I supposed to do? Oh, I'm supposed to do magic trick number 1, which is sys exit, and I happen to not need any additional inputs for magic trick number 1. Program's over. Make sense? This is a low-level implementation of Hello World, but we even in this, we see that we are leveraging the operating system to do a lot of the heavy lifting for us. Things would be so much worse if we didn't have an operating system to rely on, or if the operating system was a very, very, very old school operating system that didn't have effectively an API, a whole bunch of system calls that did common things for us, like write crap to the screen. We take that for granted, but if we had to do that ourselves every single time we wrote a program, we wouldn't be happy little programmers. Make sense? Okay, so this is what that low-level language does. So high-level code goes through a compiler, turns into low-level code. Ultimately, let me just finish this picture here real quick, and then we'll stop for next time. Ultimately, this guy turns into machine code using another tool, linker, and a couple other things. That runs specifically on the CPU. All right, so we're in the process of figuring out what's in a process. Get it? All right, I will see everybody on Wednesday.